Not simple. Harmonic motion. Okay. A pendulum, like the one that you made and used in your lab with a little washer on the end of a string, that's called a simple pendulum. And a simple pendulum obeys this simple harmonic motion. Okay, it's something that oscillates back and forth and back and forth and back and forth. So we have simple harmonic motion, which is a general description of things that oscillate back and forth in a predictable manner. It's a weird thing to think about when we talk about orbital motion. That is circular motion. That is simple harmonic motion because it has all of the properties of a sinusoidal pattern, right? And if you think about, if you were to graph, here's the Earth orbiting the Sun. If I asked you to graph the Earth's position on this axis as a function of time, this is like the unit circle, right? It would turn into cosine, right? And then if I asked you to plot it in terms of this axis, it would turn into sine, okay? And this has an orbital period associated with it. And it also has an angular velocity associated with it, omega. What's the relationship between omega and the orbital period of the Earth going around the Sun? Omega is angular velocity, right? And we know that it's how many radians per second. So if I know one thing, like how long it takes to go all the way around, that's t, how many radians is that? 2 pi radians, so it's 2 pi over the period. Does this look familiar to you? 2 pi over the period gives you what in a sine function?
B.
Yeah, the thing that goes in front of the variable, right? So if I wanted to write this out, it would be sine of omega t. But let's take a step back for a second. Let's talk about a specific type of simple harmonic motion, and that is a mass on a spring. That instead of a mass oscillating this way, it's like a mass on a table, the spring's attached to one end, and it's set into motion like this. Okay? That makes it easier because if I draw a free body diagram, now I have in this direction, the oscillatory direction, I have one force, kx. So this is the situation. You've got a mass on a spring, you pull it back, you release, and it goes back and forth and back and forth and back and forth. Now, here's a question for you. Is the force from the spring always this way? What else could it be? This way, right? If I go past the point where the spring is in equilibrium position and I compress now, the spring will push against the mass going the other way. So the direction is in the direction of equilibrium. Okay, so if I have a spring, okay, and let's say that it's not fully compressed when it reaches equilibrium. This is equilibrium for the spring. And I pull it out, then it wants to pull back, right? But if I push it in, then it wants to push out. Okay, so it always wants to return to its equilibrium position. But let's just say, for this case, kx is to the left. But we do know that the acceleration is going to be in the same direction as the force, right? The net force and the acceleration are going to be in the same direction. When we talk about things that have a force like this kx, it's called a restoring force. And we talk about Hooke's law, and that says that the force from a spring is equal to negative kx. And the negative means it's always going back to equilibrium. Okay, that's the direction of it, is to equilibrium. So if I sum all the forces that are acting on this, you've got this kx, which is, by definition, we say negative, toward equilibrium. And that's going to equal the mass of the mass times its acceleration. So this is an easy way for us to describe the motion of a mass on a spring as it oscillates back and forth. But in itself, this is not that helpful, because as it oscillates back and forth, its x, the amount by which the spring has been stretched or compressed, is changing, which means the acceleration is changing. Okay, and so you can't just figure out, oh, what's the acceleration? Let's use some kinematics or something, because this is changing. And so that makes you think what? Calculus. But it's calculus unlike anything you've ever seen before.
Fun.
Because, let's just stick with this for 1 second, but let's take a step back and let's think back to air resistance. I promise we're not going to actually go follow through an entire problem. But with air resistance, if you have something like air resistance is BV, and you've got mg going down, and you sum the forces, you can say MA is equal to mg minus BV, and then you can say A is equal to what? What is the thing that you do in air resistance problems? You replace A with what? dV dt. Right? dV dt.
So that was a regular bell.
Right.
Let's go.
Okay.
Oh, time to go.
So, what you do here is you replace this A with dV dt so that you get something that has a variable.
Disregard that bell.
What teacher is like, okay, see you later, guys. Okay, so you replace V, or you have the variable V, and you replace the variable A with dV dt. So you have a variable and its derivative, or its differential, in the same equation. This is called a differential equation. This is dV dt, but that's not helpful to you. Because if I replace A with dV dt, I still don't have like a common variable to deal with. I've got x and now dV dt, which is still useless to me. But instead of that, what can I replace A with that will write it in terms of x? Yeah, the second derivative of displacement. It's called a second order differential equation. So if I replace A with the second derivative of position, I end up with something that looks like this.
Okay.
I like what you just said, Kyle. You said okay, but you implied, so what, who cares, right? All in your tone of voice, I could read it. Okay, why does this matter? What does it mean? And I assume that you're asking, how can I solve this? How do I solve this second order differential equation? And the answer is the best answer you'll ever encounter. With this one, no. With this one, you separate variables and you integrate both sides. With this one, you can't just integrate both sides twice.
We're going to test the bells one more time. Please ignore that bell.
With this one, you have to guess the answer.
Yeah.
No way.
Yeah, you have to guess the answer. So,
No, I think that's go home.
it's probably 7. No, it's you have to think about it sort of logically.
Oh God. What type of logic? Physics logic or normal logic?
Are they not the same?
No.
Dominic logic.
There's 2 numbers in that equation. That's it.
what I would do is I would ask myself, what can I take the second derivative of and get that same thing back? Right? What this equation is saying is, let me take two derivatives of a function and get the same function back, only varied by some constant values.
Ease or something.
1/6 x cubed. If I take the second derivative of 1/6 x cubed, I get 1/6 x cubed back?
It's even to something.
Never mind.
E.
There's an interesting thought. It could be an exponential. Okay, that's one way to think about it.
Oh, or like sine.
Oh, like sine,
Oh.
right? A sinusoidal function. If you take sine, and the reason it's not exponential is because you're not just getting it back, you're getting it back but negative, right? So, so you take two derivatives of sine and you get negative sine, right? So that's the part about guess and check, right? You say, okay, well that's nice, but what are all the other parts of the sine function? I know it's sine, but a sine function is like a times sine of omega t plus some phase shift, right? This is the most general way you could write out a sine function, right? But the question is, in this particular situation, what corresponds to what here? Okay? So, you have to test it. Okay? So I have to figure out what makes this true if this is x. How would you test it?
Guess again?
Well, now we have this function. Let's plug it into our equation in both spots. Let's plug in for x, and let's plug in for the second derivative of x, and see what washes out. Okay, so if
Sadness.
on this side I have negative k times x, which is a sine omega t plus b, equals m times the second derivative of x. What is the second derivative of x? Well, let's do it, okay? T is the only variable. Okay, so if we take the first derivative of x, what do you get?
A cosine.
A cosine omega t plus v times the derivative of the inside,
You write it as dw?
which is just omega. Right? The derivative of omega t with respect to t is omega. So it's a omega cosine omega t plus v. Okay. Let's take another derivative. This is the second derivative.
Negative a omega squared sine.
Negative a omega squared sine omega t plus v.
But then that's different than the original thing you put in, because it's an omega squared.
Exactly! That's the point! That's the point of this entire thing, is that you see that. Okay, it's not exactly the same thing that you plugged in because it's not, the equation wasn't that negative x equals d squared x dt squared. You have these other things in here that you have to figure out how do they fall into the equation? Where do they fall in? So if I replace this now with negative a omega squared sine omega t plus v, then everything cancels except the k and the m and the omega squared. So that means that k equals m omega squared, or omega squared equals k over m.
So do we never have to derive this again? Because we know that, or does that change with every single problem?
It changes with every single problem, but the format, if you look at this, right, if we were to write this in terms of, if you were to solve this for d squared x dt squared, you would get d squared x dt squared equals negative k over m times x, right? K over m is omega squared, but whatever's in front of the x is always omega squared, if you solve it like this. Okay, anything that you can write out the force equation for that obeys this rule, this form of the equation, that's the second derivative of something equals negative constant times that something again, that is a simple harmonic oscillator. That's how you can tell if something is following that kind of motion. As soon as you see this, then you can figure out everything, right? You can figure out that it's oscillating back and forth, and you can figure out what omega is. And omega isn't just some like made up variable, right? We wrote it out because that's how you learn to write out what the sine function looks like. But omega is directly related to the rate of the motion of the object, right? Omega is related to the period. Omega is just like the omega for circular motion, 2 pi over the period. Okay, so this, whatever's in front of the thing that you were taking the second derivative of, your original function, whatever's in front of that is always equal to omega squared. So I can solve this for omega, which is the square root of k over m. And if I asked you to use this to solve for the period, you would just do 2 pi over omega, which would give you the period. Because omega is equal to 2 pi over the period, and the period is equal to 2 pi over omega. So the solution to this differential equation, if you're going to go back, is going to equal a sine of the square root of k over mt plus whatever your phase shift is. Okay, phase shift just tells you, is it sine, is it cosine, or is it somewhere in between? Right, how much is it shifted on your x-axis? In this class, it's usually either straight sine or straight cosine. Okay, because things that happen naturally usually either start from rest or they start with a maximum velocity. Okay, there is a relationship between the maximum position or amplitude of an object and the maximum velocity of an object. Because if the maximum position is encountered, then sine is at a maximum. Which means your velocity or your derivative of your position is cosine, which is always at a minimum when sine is at a maximum. So sine is at a maximum when you pulled it all the way out or it's reached the endpoints of its motion. Sine is at a maximum, cosine is at 0, right? When I say minimum, I mean, absolute value minimum. It's at 0. So your velocity is 0 at the two ends of your oscillatory motion, because the derivative of your position is going to be cosine, or the other trig function, the other sine function, right? So if your position is a sine function, then your velocity is a cosine function, and if your velocity is a cosine function, or if your position is a cosine function, your velocity is a sine function. They always reach maximum when the other one reaches 0. Okay, sine is also at a minimum displacement when cosine is 0. If it helps, picture the two graphs on top of each other. There's sine, and here's cosine, right? This is when it reaches maximum amplitude. This is when it reaches minimum amplitude for sine, and that's when your cosine function is 0. Okay? How about maximum acceleration? When does it reach maximum acceleration? At which points along this oscillation?
Would it be like when it crosses the X?
When cosine is 0, which is back to when sine is a maximum, right? When sine is a maximum, that's when your position's also a maximum. Which makes sense, because if you go back, forget everything that we just did, and you go back to negative kx equals ma, acceleration is maximum when x is maximum. Right? This is the biggest number possible when this is the biggest number possible. Forgetting all of the calculus that we just did. This is the largest when this is the largest. Okay? And you know that the derivative of velocity should be 0 to find the maximum for velocity. Okay. So, in terms of the position or the stretched amount of the spring, what is the position of the spring, or the mass on the spring, when it reaches maximum velocity? What is the position when it reaches maximum velocity?
Isn't it when it's at equilibrium?
Equilibrium. Right? When it passes through equilibrium, it's going the fastest. But what is the force on it when it's passing through equilibrium? It's 0. Okay. We're going to focus on masses on springs for a little bit. The derivation of this square root of k over m thing is easiest when you consider a horizontal mass on a spring oscillating back and forth. When I was showing you this and I decided to stop, right, the mg part of this makes it more complicated, but it turns out you get the same answer for the omega going this way. Okay, the math is more difficult. What changes about this is the equilibrium position. If you have a mass on a spring that's horizontal like this, the equilibrium position is the equilibrium position of the spring by itself. But if you have a mass on a spring that's stretched out like this, now this is the equilibrium position of the oscillation, and if I pull it down, it'll oscillate about the new equilibrium position. Does that make sense? So the equilibrium position is now wherever I've hung the mass, and this is the equilibrium point about which the mass will oscillate as it oscillates back and forth when it's hanging vertically.